Hello all. So let's look at wave propagation again using electromagnetic theory now. So we understood that any solution should satisfy the wave equation, right. So let's look at this wave equation itself. So how we came about this wave equation by using Maxwell. Okay. So let's look at that. So we start with the electric field representation, right, and let's do a cross operator here, right. So del cross E, so that is what we would like to do. This would become del cross B, all right. So where B is nothing but mu naught H, right. So we can also write that we know that del cross H equals dou D by dou T, and we also know D is epsilon naught E plus P. So we are going to use this. So minus dou by dou T del cross H, right, times mu naught. So we are doing this, and now we can even make it using T, all right. And let's expand this further, or D equals dou T squared. So this is basically what we have. In other words, mu naught dou squared by dou C epsilon naught E plus P. So now we have the electric field as a function of electric field and the polarization, right. So we now have a form. So that is what we would like to do from this deductions. So if some of you might be wondering, why are we doing this? The whole idea of doing this is to connecting the effect of electric field and how the material reacts to this, okay. And del cross E now equals mu naught epsilon naught, right. I'm just expanding this thing, okay. So dou square dou T square E minus mu naught dou square P over dou T square, okay. So this is our equation now. So we all know mu naught epsilon naught, right, 1 over C square here, okay, minus 1 over C squared. So basically we knew that C is equal to 1 by root of mu naught epsilon naught, right. So this is what we all knew, and then the rest of the things remain the same, all right. So when you rearrange these factors, right, we can take this factor to move to left, right. So then you get del squared, let me first write it, del cross E, right. So I'm just writing it here, plus 1 by C squared dou square E over dou T square. This is equal to minus mu naught dou square P over dou T square. Okay, so now this is a form of wave equation now, all right. So what it represents is a source, a term, right, the source that is driving the optical wave, right, and the left hand side is your electric field itself, how you can represent this, right. So basically this deduce to del squared as a generalized form, del squared U, right, that's 1 by C squared dou squared U by dou T squared, okay. So when you don't have any source inside the medium, then you can make this as 0, right. When there is no polarization inside the medium, let us say in a free space, right, there is no polarization involved, and mu naught is basically not going to play a role, sorry, then you basically get this wave equation. So, one need to satisfy this equation in order to get a propagating wave or an electromagnetic wave. Okay. So, once you have this electromagnetic wave, you want to understand how fast or how slow this electromagnetic wave is going to move. That is something that we briefly discussed in the earlier lectures on scalar wave optics, right. So, we talked about phase velocity, right, how a wave propagates through a medium, right, and how the speed is going to be changed as a function of refractive index of the medium, right. So, let us look at the wave propagation, right, using whatever we have understood so far. Okay. So, a simple wave could be represented, right, by this simple way. Let us say a simple wave, right. Let us say a simple wave, very importantly propagating, right. So, it is, let us say it needs to be propagating. So, you could represent it as a e to the power minus j k z minus omega t, right, is what you say, a propagating wave. And let us say this is as a function of time, right. There is an amplitude, and this amplitude is changing as a function of time, right, at a certain location and so on. Okay. But then if the speed at which a particular point moves, right. So, how fast this point is moving, right, is very important, right, and that means this should force this to a constant, right, in order to find that. So, that means you see no change, right, in the wave propagating through the medium. So, if you put this as a constant, then you can find out over k plus a constant, right. So, how far it is. So, now if you want to know the velocity, how far it has moved, but if you want to know the velocity, you just differentiate with respect to time, right. So, this is basically trying to find the velocity, right, and this is basically your phase, right. So, this we said phase, and how fast the phase is changing. So, if you differentiate this, you would get omega over k. So, this is a constant, so this will go away, and this is basically your phase velocity, all right. And this relates, right, your angular frequency and the magnitude of your wave vector. So, this k is nothing but your wave vector, and this is your angular frequency. So, now the phase velocity actually links your angular frequency and your wave vector, right, and there are different forms that you can use this for various application, right. And now if you are going by the material property, then the phase velocity is basically your velocity of light in the medium, right. So, this is the speed of light in free space, right, 1 over root mu naught epsilon naught, but now it is 1 over root under mu epsilon. So, mu and epsilon or relative permeability of that. So, the speed of light from the wave equation is the phase velocity, right. The speed of light and the phase velocity are identical, right, when it comes to a wave that has a single frequency, right. So, we are talking about W. all right. So what is a refract? From here you could also find the refractive index. So what is refractive index? So one of the postulates of the wave theory is that any homogeneous, isotropic and transparent material could be represented by a single constant, which is called a refractive index. So refractive index is nothing but your phase velocity in vacuum to phase velocity in medium. Okay. So basically what you are saying is phase velocity of light in vacuum, right, is c, right. So that is speed of light, and phase velocity in the medium, just now we found out that is Vp, right, that is the phase velocity, and that is nothing but root mu epsilon over root mu naught epsilon naught, right. So if you consider a dielectric, right, a medium, right. So when mu equals to mu naught, it is a non-magnetizing material, let us say, right, then this would become root epsilon, or rather epsilon over epsilon naught root. So this is basically your refractive index. So if you know the permittivity of a material, then it is basically root of that, right. So this is something that you all know, and it is a relative permeability. So if you square root of relative permeability is your refractive index, all right. And let us look at how your wave vector is going to look like. So this is the wave vector, right. So we want to know how these two are related. So now let us look at k now, right. So k equals omega root mu naught epsilon. Okay. So this is in a medium, right. So that is why I am putting it as an epsilon, while mu equals mu naught. Okay. So if this is the case, then you can represent mu omega times root of mu naught epsilon naught, all right. Oh no, I think I made a mistake here. So this is basically root of epsilon over epsilon naught, all right. So if you deduce this, what you would get is omega root of mu naught epsilon naught. Okay, I do not have space here, let me write it here. Omega root of mu naught epsilon naught, right, times refractive index n, all right. So this is how you could modify, right, whatever we have for k, and now you can look at this, right. So this is basically your free space wave vector. Okay. So that means k equals k naught times n. I am not sure whether you are able to see this. So this is nothing but k naught n. Okay. So this is your wave vector inside the medium. So wave vector inside the medium is nothing but free space wave vector with the refractive index here, right. So this is the vacuum wave vector and n is the refractive index. So as we discussed even in the earlier lectures, right, the refractive index is going to change the wavelength, right, of light, the speed of light, right, or in this case phase velocity of light is going to change, and also propagation constant, right, or the wave vector is also going to be changed because of your refractive index. Okay. So it is important to understand the effect of the material on the wave propagation. All right. So let's look at group velocity now. So this is all phase velocity, right, and there is a something called group velocity. So what is group velocity, right? So phase velocity, the term is rather straightforward to understand, because it's a single wave and also it has a phase, and the phase is moving, and the phase, how fast the phase is moving, is called phase velocity. But now we are talking about group velocity. Why should we talk about group velocity, right? So group velocity is nothing but how a pulse propagates, right? So more often we use pulses of light, right. Let's say if you have a pulse of light in time domain, you will have not a single frequency or multiple frequencies in the frequency domain, right. So a pulse in the time domain will have a broader frequency representation in frequency domain. So let's say there are waves that are propagating, so the frequency, the pulse, let's say, right, you will have a certain bunch of frequencies there. All right. And the k, or the propagation constant, is also having a spread in that, right. And you could have more than one, right. There are pulses, let's say there are two waves in this case, so there is another frequency here, right, and it will have its own wave vector here. Okay. So let's say this is k plus minus delta k, right. So it has a certain spread, right. So there are two waves, right, in this case, but then it has a certain spread, that's fair enough. But what about the amplitude, right? So you could have two different amplitudes, but for simplicity's sake, let's assume that the amplitudes are equal, right. If amplitude of both the waves are equal, let's say E1 equals E2, let's say. All right. So now I'm going to put these two waves together, right. So if I'm going to put these two waves together, then I can write this as simple addition, right, of cos and sine terms plus delta omega t minus k plus delta k times z, okay, plus the second wave cos omega minus delta omega t minus k minus delta k c. So this is how your wave is going to propagate. All right, a very simple cosine representation. We said the wave is moving together, so they are moving together, that means how it's going to look like. So you can rearrange this, right, simply, right, because the k terms are going to go away here, right, and they are going to add up, right. So minus k becomes 2k, and the factor 2 you can take it out, right. So now you can write two waves as simply like this. Okay. This is just an identity function, right. Cos x plus y plus cos x minus y, right, will be equal to 2 cos x cos y. Okay. So this is just an identity that I applied here, and when you apply this identity, right, you get something of this kind. So what all this delta k and delta omega, right? So this is your beating, right, of these two waves, right. It's called temporal beating, and this is spatial beating. So beating is nothing but interference of these two waves, right. So there are two components, they are beating with each other. So if you look at beating, it's nothing but, you know, what is the beat length, right. So temporally how far or how these guys are beating. Okay, so that is the two beating factor, right. So now one can represent the wave that we just saw as a function of time, right. This is 2 yeah, 2 E naught, I missed that one. Okay, so let's look at the similar way how your distance can be done, right. So you know the frequency, you know the term here, right, plus constant, right. So this the same trick that we applied earlier on. Okay, so delta omega t plus delta kz, right, should be equal to constant, right. So we took it from here, right. So you don't have to worry too much. This is same from the phase discussion that we had. All right. So if you want me to write, I can do that. Delta omega t minus delta kz should be equal to a constant. All right. So now that is what we are using here in order to find the speed at which this this wave is moving. Then we have to differentiate with respect to time, right. If we do that, then this becomes delta omega over delta k, right. So the constant is gone, or in other words, dou omega over dou k, which is nothing but the group velocity. Okay, so you see now when you have a group of waves, right, or pulses traveling, right, then it's not anymore, you know, single frequency that is dictating the speed at which the wave is moving. Now it is this bunch of, you know, the spread, the bunch of frequencies are moving together. If that is the case, then you will have, you know, a group velocity instead of phase velocity. All right. So the velocity at which this group of waves move together, okay, they are moving together, right, they are not splitting, they are moving together, but that speed of that movement, that bunch or that envelope is different. So we normally represent it that beating, right. So you can see here there is an envelope that you can see, right, as you move along, right. So you can see there are two waves here, right. So one is at lower frequency and one is at higher frequency. You can see this is omega 1 and this is omega 2, right. So when you have this together, right, it's almost like modulated signal, right. So how is the modulated signal going to propagate through? There are two frequencies that you are mixing together. So how they are going to propagate? So that propagation is given by this group velocity. So but you can, you know, just deduce this group velocity to phase velocity, you know, really quickly, right. So when d omega over dk is a constant, right. So when you don't have this delta omega, right. So if the delta omega goes to 0, then d omega over dk becomes a phase velocity now, right. So in vacuum your phase velocity equals to group velocity. In vacuum your phase velocity will be equal to group velocity, right. So they are all these waves are, you know, there is only one single wave and you don't have to, you know, worry about the group velocity in this case. Okay. But then in some complex medium, right, this can be a little you know, complicated, right. So we saw in this case, you know, your your k, right, is represented quite easily through omega n over c. So this is your in a, let's say, in a complex medium, your k can be written as follows, right, omega n over c. All right. So we know the group velocity here, the omega over dk, right, but we know the k, so let's invert this and we will use whatever we know about k, omega over c. So if we use the differentiate this equation n over c, so this is one term and the next term is omega c over dn over d omega minus 1. So this is the group velocity, right, that we see here. So if you can rearrange this group velocity, you can nicely represent it in this form. So we are just changing your omega to n by just moving around the terms, right. So this is basically k over omega is equals to, you know, n over c, right. So omega equal to ck over lambda, right, for some of you who might want to refer back. All right. So this is your group velocity when it is propagating through a medium. Okay. So the medium is now interacting with the wave and it is slowing down, right. So the c is your free space wavelength, right, sorry free space velocity, and this is your reduction factor. So earlier on we saw the phase velocity, right, is nothing but c over n, right. So whenever material is propagating through a medium, right, the speed of light is going to be reduced proportionally to the refractive index n. But then when you look at this, it also represents the same, but then the denominator is a little complex. So we have n, right, but then there is an additional factor dn over d lambda, and this is what we call dispersion or chromatic dispersion. So the refractive index, right, is a function of wavelength. Okay. So because of this, your group velocity, right, is going to be a function of the wavelength that you have in the wave that is propagating, or this group of waves that are propagating. So if the wave if the two wavelengths are going to be there, one will go faster compared to the other. Okay. And this is the property that we use in lot of, you know, pulse compression and pulse stretching and all those kind of interesting applications, right. So this dn over d lambda, right, can have two slopes, right. So dn d lambda could be, you know, less than 0, right, or you can have, you know, greater than 0. So when it is less than 0, we call it as normal dispersion, and when it is greater, we call this as anomalous dispersion. All right. So when dn over d lambda is 0, we call that as anomalous dispersion. In this case, the group velocity, right, will be less than the phase velocity. All right. So they will always move in that direction. All right. So this is an important relation that you may want to, you know, pay attention to, right, where your group velocity depends on the refractive index of the medium, right, but an additional term, right, because it is a group of waves, right. So and these waves will have different wavelengths, let's say, right, and because of this difference in the frequency or difference in the wavelength that you have within this bunch of waves, you are going to experience, right, an additional factor or additional reduction factor in the velocity equation that we saw, right, a group velocity equation we saw. So we have negative sign here, right. So based on the sign of dn over d lambda, you could make it faster or slower. Okay. So you can never get it faster than c, but the reduction factor can be managed by looking at whether this dn d lambda is positive or it is negative. We will see that quickly in light matter interaction, where you will have both anomalous and normal dispersion when you look at the material properties. But just to keep in mind that one could actually if there are two waves, one wave could be traveling faster than the other wave, right, and in that case, right, you will, let's say if these two are lambda 1 or let's say omega 1 and omega 2, right, and if it travels after a certain distance, you can either make them far apart, right, this is as a function of time, right, these waves can move apart, right, or you can bring them closer, right. So these are all two possibilities, and this bringing them closer or putting them far apart depends on whether this slope is positive or negative, as we just discussed here, whether you are in normal dispersion or you are in anomalous dispersion. All right. So with that we conclude this dispersion discussion, right, and I would like to briefly talk about how this dispersion is important, right, when we look at electromagnetic wave interaction with any matter for that purpose. Okay. So when light is propagating through a medium, right, so the medium is characterized by its dielectric constant, its polarization and its magnetization, all those properties there. So basically you have atoms inside the system, right, that is looking for this energy that is available. Okay. You can take it out, right, or it can interact with the electromagnetic energy inside the system, and they could couple, right. So it can take out energy and it can change the property of the light itself, right, using the energy that it absorbs or intrinsic properties itself. So there is a lot of interesting light mat interaction happens, right. So one of the basic material property that we need to understand is what is the origin of this refractive index in itself, right. So we just said it can be characterized by refractive index n, right, and we also saw how the refractive index affects the material. But where is this refractive index coming from? Where is this resistance to flow of light is coming from, right? And this is coming from the microscopic nature of the material itself. Let's look at how one can view or conceptualize this refractive index of the material. Okay, so that is where we would understand the light and matter interaction. Okay, so let's look at what happens if you take a material, right, and you put a certain electric field into the system. Okay, and when you put this electric field and it is a dielectric, right, and what this electric field or energy is going to do is to create a dipole. So there is an induced dipole, what you call, right. So there is an induced dipole P that is represented, that depends on the electric field that you apply, but then there is polarizability of that electric field. This is a very important characteristic, right. This is atomic polarizability, right. So this is derived from the classical electron model. Okay, So you must have come across this in your solid state physics courses, right? So the polarizability, right, how much you can polarize this material, right, depends on this alpha, right, and the electric field E, right. So the polarization, the net polarization, right, depends on the number density, okay. So number of dipoles in the system to the induced dipole, all right. So in other words, n, so this is small p, let's say, okay. So I don't want you to get confused. So this is small p and this is capital P. So this is what you have for the polarization, right. Or in other words, one can do this as susceptibility as well. So this is nothing but susceptibility. So epsilon naught chi times E is your polarization. And what is epsilon? Epsilon is nothing but epsilon plus epsilon naught times chi, right. And if you take this, 1 plus chi is what you have, all right. And from the earlier equation we could write 1 plus n alpha times epsilon naught, right. For a non-magnetic material, let's say, for a non-magnetic material, what happens? Your mu becomes mu naught, right. So then one can write the refractive index n squared is nothing but 1 plus chi, in other words 1 plus n followed by epsilon naught. So now your refractive index now, right, depends on the number density that you have inside the medium, or the number of atoms that you can polarize inside the medium, and the polarizability, right, the ability to polarize something. There are some material that you won't be able to polarize, let's say. So what is the polarizability of this material? We'll quickly see what this alpha is just going forward, and then the epsilon naught, the free space dielectric constant, all right. So let's look at a classic electron model, right. Some of you might have already done this. Since we are reviewing our past electromagnetic knowledge, let me just also review this classic electron model, okay, from where we understand the susceptibility, what is the origin of susceptibility, and also how we relate the refractive index, right, to the material resonances and so on, okay. So so let's look at the classic electron model, right. In a classic electron model, what we are doing is we take an atom, right, and then we are inducing this atom, or let's say we are eliminating this atom with a uniform electric field, right. This electric field of this form, right. So the electron here, right, so you are putting into an atom, but then there is an electron associated with this. So you have the nucleus, and then there is an electron sitting somewhere. So when you apply an electric field, right, because the electrons react to this external field, right. So there is a work done on these electrons, right. So the electrons are bound to this nucleus through the Coulombic force, right. So you have a force that is reacting, right. So it is keeping the electron within the atom here, right. But now you are having an external energy given to this electron. So this electron is going to take this energy and trying to oscillate, right. So it is going to move around, right, and that is going to create an additional energy. So now there is a restraining force that is going to pull this back, right. So there is an external field, but then there is a a force to pull the electron into the influence of this, right. So what we can do is we can easily figure out the force balance here to see how one can write this. So there is a force coming from the electrical field, right. So that is E electric field in the local, so not the global one. So there is a local electric field, plus there is a force from damping, right, because that is the restraining force, and there is a force from the spring, all right, and this is all equals to ma, right. So mass times acceleration, so the mass of the electrons and the acceleration that this electron is moving. So we can simply write this, let's say if r is the distance, right, that we have. So this is the nucleus, this is r is the distance, dr over dt square plus, right, m times, this is the damping, dr over dt plus a constant term, right, and this is equal to the force that you are applying, right. So this is E, that is the local field, e to the power of minus I omega t, okay. So this is minus I omega t, all right. So the dipole moment of the system, so what is the dipole moment of a system, very small system. So this is basically E times or charge times the distance. So this is your dipole moment of the system, all right. So now what one could do is we can simplify this, right, and this is all second order PDE solution that we all know, right, a steady state solution for this, right. So let's say the steady state solution for something like this would look relatively easy. Let's say you have R, okay, which is nothing but as E times m omega naught square minus omega squared minus I omega gamma. So how did I get omega here? Is through this transformation where we write m d squared by dt square x plus m gamma times d by dt times x plus m omega squared x, okay, which is equal to E times E, okay. So if that is the case, then I can write this as x, okay, and this is the solution that we have, right. So we know the induced dipole. So now we have a solution for x, the induced dipole. So let's move to the induced dipole. So the induced dipole P equals minus E times x here, right, and that is nothing but E squared m omega naught squared omega squared minus I gamma omega times E now, all right. So this is our induced dipole, right. So from the induced dipole we could calculate this alpha, right. So the this is nothing but alpha, right, without the electric field there. So the alpha is nothing but E squared m omega naught squared minus omega squared minus I gamma omega. So this is our alpha term, all right, and n, of course we will come to that n little later, but now you can already see that where we are getting at, right. So if n is atoms per unit volume, So we said number density, right? Then the refractive index, right? So the refractive index we saw here, right? So n squared, this term, n squared equals 1 plus n alpha divided by epsilon naught, right? Divided by epsilon naught, right? So let's just substitute this. That means n e squared divided by epsilon naught m omega naught squared minus omega squared plus I. Okay. So this is what you get when you have when you represent this n squared as a function of this, right? Let us look at this a little bit more carefully, right? The denominator term here, it's a solution that we already know of, but there is a condition that when these oscillations are rather small. So if this is rather, let's say, very small value, let's say, right? This is for small values, right? And then it doesn't make to look at n. So you could look at just n squared instead of n squared, you look at n, right? So this is for small values of this, okay? Then you can write this as 2 epsilon naught m omega squared. So now you can see the refractive index, right? So the refractive index depends on the material properties, right? So what is this material property? So it depends on the number density, right? How many atoms are there per unit volume? It is directly proportional. So what that means is when there are more number of atoms per unit volume, right? So I take two material system, so where the atoms are sparsely situated, right? So there is a lot of distance between them. So that means the number density n is very low. But then I could take another material system, right, where there is a very tight packing of these atoms, right? That means for a given unit volume the number of atoms are more, right? So if I say this is material Nb and this is Na, so Nb is much greater than Na, right? So the number density is higher. So what this implies is the refractive index of B will be also greater than refractive index of A, right? So a material which is denser, right, will have higher refractive index. You can go back and check, cross check this with different materials, okay? Look at their number of atoms per unit volume with respect to the refractive index. You will see this happen, right? And the other thing is the frequency of oscillation, right? So this omega is nothing but the frequency at which your electrons are oscillating, right? So there is a oscillating frequency there. So your refractive index also depends on those oscillation, right? So if you know the number density and the frequency of oscillation, you will be able to understand what is the refractive index, okay? So let's look at what should be the refractive index of air, okay? So air at 0 degree C, right? So the number density, probably this is a popular number that you all know, right, per meter cube. So this is the number density, and the resonance frequency is 4 pi 10 to the power of 15 per second. So this is your oscillation of this. So when you plug this number in, right, this actually comes around n equals 1.0003, right? So we say free space refractive index is 1, right? The vacuum refractive index is 1, right? But then air has its own number of atoms inside the system. So when that happens, then your n is 1. So when the number density is 0, right? So n is equal to 1 plus this some quantity here, right? So which depends on n. So when there are no atoms present in the system, then n is equal to 1. But air will have molecules present in it. So it could be nitrogen molecules are there, water molecules are there, right? So you will have these molecules there, right? And there is a density to it. And also the air density varies based on moisture and so on, right? So if you look at air in Bangalore and air in Chennai, air in Delhi, they are all different, right? The reason is it could be pollution, it is also a local weather and so on, right? So the refractive index of air, right, will change based on the number density here. So this is how you relate the material property with the refractive index of the material. Okay, so that brings us to understanding the dispersion now. Okay, so let's look at the dispersion. We understood that it depends on the frequency of oscillation and everything, right? Let's look at how the refractive index, right, creates this dispersion, right? So let's look at dispersion in this medium. Okay, so we all know that the refractive index is represented by this form. So mass of this electron, and then you have this oscillations, right, of the electron that is having, right? So this basically we call this as a dispersion equation. Okay, so when omega increases, right, so the omega naught is the fundamental frequency of the oscillating electron, right? And then omega is the external, right, frequency that you apply, let's say, right? That is the electric field frequency that you are giving as an input, right? So that is what we saw here, right? So we are giving some external electric field omega, while your omega naught here is your fundamental frequency of the system. Okay, so let us look at that. Did I do anything special here? No. Okay, that's good. I think probably there is a sign issue here, so this should be plus. Okay, did I miss it anywhere? Yeah, so this is a plus here, right? Pardon me for that. For some of you might have already noted it. If you have not, so just make that correction. Okay, so once we have the dispersion equation, then we understand, try to understand what happens to the material when the input frequency is changed, right? So let's try to look at that. So when the omega here, right, so we are looking at this, right? So omega naught square minus omega square. So when I am increasing this omega, right, and it becomes very close to omega naught, okay, so what will happen, right? So when you have this particular term very close to omega naught, right, then the refractive index will shoot up. All right, what you are trying to do is you make this denominator term, right, going very close to 0, right? So provided that the mass of electron is also small, and then the damping is also pretty small, let's say, right? When the omega is very close to omega naught, the refractive index increases. Okay, so this is one of the reasons why you're in a prism, your blue light bends more than the red light, right? So when you take a prism, right, when you have white light, so your blue light comes out here, your red will come out here, right? So blue light sees higher refractive index compared to red light. Red light say lower refractive index, right? It's relative, right? It's not low refractive index compared to the blue light. The reason for that is this, right? blue light and red light, they have different frequencies, right. So when the frequency is very close to omega naught, so omega naught, it's a natural frequency of oscillation. When they are very close to it, then you see that your refractive index actually increases, right. So what happens to the imaginary term, right. So the imaginary term here, right. So the imaginary term is nothing but the damping term, right. So this I gamma omega is nothing but damping of the electron motion, right. It is trying to restore it, and this is what causes absorption. So when the light is propagating through the medium, right, at certain frequencies you will see that you start absorbing, right. And that is again an interesting way to look at this the dispersion equation. When omega becomes very close to omega naught, right, that is when you see the effect of the imaginary part, right. So the imaginary damping is smaller, right. So the imaginary part becomes more important, right. So gamma omega becomes more important when omega reaches omega naught, when close to the resonance or close to the resonant frequency of this device or resonant frequency of your material, then you see damping take over. So that is when you see absorption starting to happen, all right. So let us look at how one can represent that. So because you have the imaginary term here, right, so then you can write the refractive index as a function of as a complex number basically, okay. So let us say n is the refractive index, you can write n as n minus ik, all right. So I is your damping or extinction coefficient, n is the real part of the refractive index. So this is real part and this is the imaginary part, what we call extinction coefficient or absorption, right. So you can take this dispersion equation and then you can split the real and imaginary parts. If you do that, you will get something like this. Minus, okay, so this is the real part and then the imaginary part starts here. All right. So now you can see the real part of the refractive index and the imaginary part of the refractive index very clearly, right. So you can actually try to plot this one, right. When you try to see when omega becomes very close to omega naught, right. So this whole term, right, becomes close to 0, right. It's reaching 0, right. And on the other hand, the imaginary term here, right, when omega reaches omega naught, this is reaching infinity, very large number here. So this term becomes 0 and all you get is 1 over gamma square, right. So not necessarily infinity, the number is pretty large, okay, because it's 1 over gamma squared now, okay. So when omega reaches omega naught, you are getting a very large value of k, right, while n becomes small, okay. So if you were to draw this as a function of omega minus omega naught, right, and this is how it would look like, and this is your resonance. Okay, so this is what you see. Your K will become very large at resonance, right? So when omega reaches omega naught, right? So this is where you have the resonance, and then the refractive index n. So this is K, and your refractive index would do something interesting. So it will so this is n minus 1, let's say. Okay, so this is how it looks. As you can see, right, at resonance, right, your refractive index is rather low. Okay, it's but then your K value is very high. Okay, but then outside the resonance you will not see much. So you don't see the effect of K at all. So it's rather low. It is dominated by the refractive index. And here again you can see two slopes, right? So you see a positive slope, and then you see a negative slope, right? If you remember, we talked about dispersion, right? dn over d lambda, right? We talked about dispersion, and we talked about anomalous dispersion and normal dispersion in the material, right? That is actually originating from this nature of your refractive index curves. Okay, so that brings us to the end of our discussion on how the material properties, right, is dictating the refractive index. So what is the link between these two? So material, they got their own atoms, and electrons are vibrating at certain resonant frequency, and when you put an electric field, right, at a certain frequency into the system, then the electrons are going to look at it. That's basically the polarization that we talked about, right? So they are going to take this energy, and then they are going to oscillate even more. So that energy it is taking, right? So there is a relation between the frequency that you put in and the frequency of oscillation, and when these frequencies are very close to each other, then there is a lot of absorption happening, right? It's not, so that's the reason why we say refractive index is complex, right? It is not a real number alone. So it has a real part and then the imaginary part. So the real part tells you about the number density, right, that you have, the density of the material. Primarily it is dictated by that, but then the absorption strongly depends on how far you are from the resonance, right, or resonance of your vibrating electrons. And there are different type of resonances. So in this case we only looked at the electron resonance, but you also have resonance from the phonons. There is a lattice vibration that happens, and also we have absorption from the electronic levels, right? So there are different absorption phenomena or resonance condition inside the material. What we today discussed in this lecture is only the resonance coming from the electrons there that is oscillating. There are different resonances, so they will all have different frequencies. So that is the reason why, when you look at the absorption spectrum of a material, you will see peaks coming at different position of frequencies, and these frequencies are representative of different processes of absorption. There are ionic absorption, right, electronic and phononic absorption. So this is all different absorption phenomena that makes the refractive index complex, and later on in the course we will see how this complex refractive index is affecting light propagation through waveguides, right? If you have how light is getting absorbed as it propagates through the medium. Okay, so with this we have covered or have done a review of the basic things that we need in order to progress in the course, right, of how a wave is represented and how the material properties affect the waves, and how the material property in itself can be understood, right, from the microscopic scale. With this we have completed our review. In the coming classes we will move towards understanding photonic integrated circuits, the components and all the nitty-gritties. Thank you very much for listening.